Now we're going to look at the energy. Now that we have a fundamental understanding of what radiation is, we're going to turn to the topic of black bodies. Now, the concept of black bodies starts here. All objects in the universe emit radiation. Everything, absolutely everything emits radiation. Obviously, the sun emits radiation, but the earth also emits radiation. And believe it or not, you and I emit radiation. Just sitting in a room, we are emitting energy away from us through radiation. Now, the wavelengths of radiation given off by an object depend on the temperature of the object. That's what we're going to see. But when they do, they tend to create a curve. Let me create a laser pointer here so I can show you. This is the black body curve for an object similar to the sun. Now you can see that ultraviolet, it emits a little bit of that radiation, but then all of a sudden it peaks, and the majority of the radiation given off by the sun is visible light, and then starts to drop off. There's still a fair amount of infrared radiation given off, but far less than visible light. Microwaves, it still gives off a little bit of microwaves, but not much. TV waves, radio waves, very little. So you end up with this curve that has a peak that indicates the type of radiation it gives off the most. This is what we call a black body curve. Now I'll compare this black body curve to what happens in all actuality, and you'll see it's fairly similar. Okay? Now, the peak wavelength specifically can be determined using what's called Wien's law. Wien's law says that the peak wavelength of radiation given off by an object is 3,000 divided by the temperature. The temperature here must be in Kelvin. If you put in Fahrenheit or Celsius, you're going to get something that does not work at all. Not to mention, if you have Fahrenheit or Celsius, there's a possibility of negative temperatures. So you could have negative wavelengths, which just doesn't make sense. Okay? What you need instead is a temperature in Kelvin. It's the only unit of temperature that will work in here. When you do this, take 3,000 divided by the temperature in Kelvin, then your answer is going to come out in micrometers. Now remember, micro means 1 out of a million. So a million micrometers is equal to 1 meter. Sometimes we give this answer in nanometers instead, such as in visible light. We saw in the last video that visible light is roughly 500 nanometers. How does that compare? Well, 1 nanometer is 1,000th of a micrometer, meaning that there are 1,000 nanometers in 1 micrometer. So just to see how that compares between micrometers and nanometers. All right, so there you go. That's Wien's law. And we're going to do an example in the next video of how to use Wien's law. Another principle that's important is how much energy can be given off by an object. And this law is the Stefan-Boltzmann law. And it describes the total amount of energy emitted by an object. And here you have this interesting equation that the amount of energy given off in a matter of time is going to be some number. This is called the Stefan-Boltzmann constant, and it has a value of 5.67 times 10 to the 8th watts per square meter per Kelvin to the 4th. It's just 5.67 times 10 to the 8th. That'd be 567 million watts given per square meter, essentially is what that's saying. This E thing is called the emissivity. This determines whether we're a black body or not. The area that is emitting the radiation is A, and then T would be your temperature, again in Kelvin, to the power of 4. Now, if we have a black body, this emission rate, this little E thing, is actually going to be equal to 1. In that case, we're dealing with a black body which perfectly absorbs radiation at selective wavelengths, and then it perfectly emits radiation at a specific wavelength based on the temperature from Wien's law. right? That's where we get that. So a black body perfectly emits radiation, perfectly absorbs radiation. So we get an emissivity of 1. So now our little e thing is just 1. Now let's just also assume that we have an area of 1. We're going to simplify this equation a lot. From this point on, you don't have to remember this full equation. All you have to remember is this right here. This equation right here. I'm sorry, that red on the blue doesn't work so well. We'll do a yellow from now on. So energy per unit time, the amount of energy given off in a certain amount of time, is just going to be that constant, 5.67 times 10 to the 8th, times the temperature raised to the 4th power. Again, temperature has to be in Kelvin for this to work. Okay? And that's it. So we have the Wien's law, which says that the peak wavelength is 3,000 divided by the temperature in Kelvin. And the amount of energy given off is going to be this constant number times the temperature to the power of 4. And those are the two equations we're going to need for black bodies. Now, how good is black body theory? Because, I mean, nothing can perfectly emit radiation or perfectly absorb it. There's going to be some imperfections in that. But actually it gets really close. In these two graphs, I'm showing the black body curve and the actual radiation emitted by the sun in the figure on the left and by the earth in the figure on the right. On the left, this curve with yellow under it, that's the perfect black body curve, what we've been looking at so far. Then, if we put a satellite out in space between us and the sun and detect radiation, we get this orange curve. This orange curve depicts the amount of radiation that's given off by the sun by wavelength. And you can see that it actually matches very closely to the black body curve, the theoretical curve. What's this thing down here that's black with the colors in the visible wavelength there? This is what we actually receive at the surface of the Earth. Why is it so different? It's because of the atmosphere. The atmosphere is going to scatter some of that light. It's going to absorb some of that light. It's going to change the amount of radiation so that not all of it actually reaches the surface. And so that's what this curve is. And we don't need to worry about that, but do know that that all actuality of what the sun emits really does match closely to what the black body curve says. Now, the figure on the right, this is the radiation emitted by the Earth. The red line here is the curve that we get from black body theory, and these are the actual numbers that we measure just looking at the Earth and seeing what it emits. And so you can see that even though black body theory is not perfect, it's pretty close. And so we can use this black body theory to actually describe more about the type of radiation that we have to deal with from the sun and from the Earth as well. And this will come in very important in the next lesson when we talk about greenhouse gases. Now, in the next video, we're going to do some calculations and show how to use these equations in black body theory and show what is the peak wavelength of light given off by the sun and the peak wavelength of radiation given off by the Earth.